In this video, we'll be covering question 5, which is distinguish between parametric versus non-parametric models and supervised versus unsupervised learning with examples. So let's see this one. Yeah. So parametric models assume a fixed functional form with a finite set of parameters. Basically, what it does is it assumes the form of function in advance, and based on that, our problem boils down to finding or estimating the parameters only. Here, pros are it is simple, fast, and easy to interpret. Yes, and the cons are that if we miss any type of relationship or any if we made a wrong assumption, that it then it could lead to bad prediction or a very large distance prediction. That is a very wrong prediction, right? For example, parametric models that assume about a function shape size are linear regression, which means that there should be linear relationship between feature and target vector, logistic regression, which assumes that probability, and then naive Bayes, which assumes that features are independent on each other, right? Then we have non-parametric models that makes few or no assumption about functional form, and often it grow complexity grows as the data grows. It is more flexible and can model complex relationships, right? But the only con is its risk of overfitting. For example, KNN, which is k nearest neighbor, it does not make any assumption about function or data set, right? And it is also called as non-parametric model. Then we have decision trees, random forest, density function, which is radial basis function that often does not make any assumption about the dataset, right? Now let's discuss supervised versus unsupervised. Supervised learning, in supervised learning, our training data has inputs plus target vectors, and our goal is to learn the mapping from X to Y. Often, supervised learning is done to predict a categorical value or a numerical value. For example, it is often does for classification, where email is spam can be classified based on spam versus non-spam. We can use it for logistic regression for classification. We can use support vector machine. We can use random forest classifier. It is also used for regression for predicting the house prices based on the features, right? Then we have unsupervised learning. In unsupervised learning, the training data we provide is only input features. Here, we provide only input features X and no labels or no target vectors are given. Our goal is to discover the patterns, relationship between the data so that we can make certain assumptions about that and or visualization about that. For example, when you get a data set, our first thing to do is we either perform clustering or we perform dimensionality reduction for reducing the irrelevant features, and we perform clustering to visualize the data and to see if what are the relationship between data and what are the clusters that are in the data. And often hierarchical clustering is used for dendrogram visualization, which is better and basically first step for our data visualization, right? This covers our supervised versus unsupervised. Now let's see B part. Define accuracy, precision, recall, F1 score, and illustrate their computation using a confusion matrix. Okay, so let's see classification matrix. Here, this is a confusion matrix given, that is actual yes, actual no, predicted yes, predicted no. Here, if it is actually yes and if it is predicted yes, then we will get true positive. Similarly, false negative, false positive, and true negative. Right? Here, let's discuss about the different matrix. Our first matrix is accuracy, which tells the model accuracy if the prediction is correct or not. Overall correctness, right? Which is TP plus TN, the number of time it predicted yes, a number of time it predicted yes, and it is actually yes upon all of them, right? These are all of them. And precision is basically for positive predictive value. Here the formula is TP upon TP plus FP. Recall, often known as sensitivity. Here we tell how many actual positives we find in the data or how many positives are there for all positive instances. Here the formula would be TP upon TP plus FN. These are based on the confusion matrix. And then F1 score. F1 score is basically harmonic mean of precision recall, which is 2 into P into R upon P plus R. Now let's take a numerical example where we have TP is equal to 40, FP 10, uh, Fn 20 and Tn 30 and total the 100. Now let's calculate accuracy, which is Tp plus Tn 40 plus 30 and whole upon 100, because when we sum them up we get 100. Now the value we get is 70 by 100, which is 0.70. Similarly, we calculate precision, which is Tp upon Tp plus Fp 40 plus 10. Then we get the value as 0.80. Similarly, we calculate recall, which is Tp upon Tp plus Fn. We get these values, put on the formula, and we get as 2 by 3 or 0.67, right? So these are the classification matrix. These are often used in class for evaluating a classifier, and this tells if a model is performing good on classification. If I talk about accuracy, it is not a good metric over recall and precision, because a model can have, for let's say, a model is uh, classifying a disease which is a rare disease. Now, a model can have an accuracy of 99%, but precision and recall scores would be less. This is because the disease would be rare and it would not be predicted that much. So the model just take the imbalance class, and based on that accuracy, just get the 99% accuracy, which is wrong. So we consider better metric, that is precision and recall over accuracy, right? So these are the classification metric. I hope you find this helpful. Thank you.